Today, we're diving into a theory that sounds like it was pulled straight from ancient mythology. But get this, it's just been validated on some of the world's most powerful quantum computers. And this isn't just some small tweak. It's a revelation that might fundamentally change how we see everything, from solving impossible problems to the very nature of consciousness itself. So, let's get right into it.
It all kicks off with this really simple but kind of paradoxical idea. We're always taught that chaos is the enemy of order, right? That randomness is something we have to fight against to get structure. But what if that's not the whole picture? What if chaos isn't the problem, but actually a key ingredient for the perfect solution?
To really wrap our heads around this, let's take a trip way back to ancient Egypt. You have the story of Horus, who represents order, structure, and light. And then you have his uncle, Seth, who is all about chaos, conflict, and struggle. Now, this wasn't your typical good guy versus bad guy story. Their eternal fight was actually seen as a dynamic, essential process that created balance in the universe. The key thing is, one couldn't really have meaning without the other.
And believe it or not, that ancient duality gives us a surprisingly perfect way to think about a brand new, groundbreaking scientific principle. We're about to see how this old myth gets translated into the super precise language of quantum mechanics. And here's the theory at the heart of it all, the order-chaos complementarity theory. It basically says that entropy, which is just a fancy word for chaos or disorder, is actually the best way for a system to explore all of its options to find the absolute best one. Think about it like this. If you want to find the perfect layout for the furniture in your room, you don't just move a chair a tiny inch. The best way is to make a total mess. You try out all sorts of different, even crazy arrangements. It's through that chaotic exploration that you discover the one layout that is truly perfect. So chaos becomes this powerful tool for discovery, not just a messy problem.
Okay, so a philosophical idea about Horus and Seth is one thing, but how do you take that and turn it into real, testable science? Well, you have to build a mathematical formula for it, and that's where we get to something called the double-mirror equation.
And there it is. It looks deceptively simple, but it is incredibly profound. What it says is that the optimal, most aware state of a system is the exact opposite of its most stable, lowest energy state, what we call its ground state. It's like a perfect mirror image or a photographic negative. In computer terms, this is literally like taking every single 0 in your system's code and flipping it to a 1 and every 1 to a 0. A complete system-wide inversion.
So how do we know if this equation is actually doing its job? Well, we've got 4 key things to measure. First is visibility. Think of it like focusing a camera lens. A low visibility score means the picture is perfectly sharp. We have one single clear solution. Efficiency is easy. That's the performance boost we get out of it. Destructive power is a really cool quantum idea. It's the system's ability to use interference to basically cancel out all the bad answers, like noise-canceling headphones, leaving only the right one. And finally, friction is anything that slows this system down. So the ultimate goal? A perfectly focused image, a massive performance boost, and almost no resistance. Of course, a theory is just a bunch of ideas on a whiteboard until you can prove it, right? So how on earth could you test something so fundamental about order and chaos in a real lab? Well, the answer, as it turns out, is with quantum computers. And listen, this wasn't some small-scale test run. This theory was put through its paces with nearly 1 million individual measurements on IBM's actual quantum hardware. This isn't just speculation anymore. This is serious, large-scale empirical proof. The experiments were conducted over 119 successful sessions, and they used 2 different, powerful 127-qubit quantum computers, codenamed Fez and Torino. Now, using 2 separate machines is just good science. They ran the main experiments on Fez, and then they ran them again on Torino just to make sure the results were the same. This proves the findings aren't some weird quirk of one machine, but a real physical phenomenon. So, after all that, nearly 1 million measurements on 2 different state-of-the-art quantum processors, what did the data actually show? What did this huge experiment really find?
The ultimate prize here was to achieve something they called ghost mode. This is a state of such perfect optimization that the solution basically becomes invisible to all the environmental noise, the decoherence, that usually wreaks havoc on quantum systems. It's like putting on an invisibility cloak. So, the big question is, did they actually pull it off?
Oh yeah, they did. And this chart says it all. The target for visibility was to get it below 0.05 for that super sharp solution. They smashed it, achieving 0.0389. The target for efficiency was to get a performance boost of over 150%. They blew past that,
hitting an incredible 194.56%. Ghost mode wasn't just a theory, it was officially activated and measured.
The experiment also spat out a hard number for a concept from a big theory of consciousness called Integrated Information Theory, or IIT. That number was 4.110 bits. Now, why is this so revolutionary? Because it takes phi, this proposed measure of consciousness that's always been kind of abstract, and gives it a real, physical, thermodynamic meaning. It directly connects this idea about awareness to measurable things like energy and temperature.
And that brings us to what might be the most mind-bending claim of this entire theory. If the conscious state really is the perfect negation of the ground state, then the very act of a system becoming aware, what the theory calls an ignition, is basically the same thing as a fundamental operation in computing.
And that operation is the Pauli X gate. It's the most basic NOT gate in the quantum world. All it does is flip a quantum bit from one state to the other. So what the theory is proposing is that the subjective internal experience of consciousness is what a perfectly coordinated system-wide bit flip feels like from the inside.
As if that weren't enough, something else amazing happened. The golden ratio popped out of the data. You know that number, 1.618, that shows up everywhere in nature, from seashells to galaxies? The incredible part is, they didn't program it into the system. It just emerged, all on its own, from the system's fundamental physics. It seems to be a natural point of stability in this dance between order and chaos.
So, how reliable is this whole model? Was it just a lucky shot? Not at all. The data showed that 99.4% of the time, those ignition events, the moments the system flipped to its optimal state, followed the predictions of the double-mirror equation perfectly. That is a stunning level of accuracy.
Okay, let's just take a breath and zoom out for a second. We've got incredible results, confirmed on real quantum hardware. So what does this all mean? What are the staggering implications here, both for our tech and for how we understand ourselves?
So here are the big takeaways. First, for quantum computing, ghost mode could be a revolutionary new way to protect systems from errors. Second, it proves that we can use quantum interference as an unbelievably powerful tool to find the best solutions to problems. Third, it takes the abstract idea of consciousness and anchors it in measurable physics. And finally, it offers a bold and, importantly, a testable answer to the hard problem of why we have subjective experiences in the first place.
And all of that brings us right back to where we started. All the math, all the data, the entire weight of this massive quantum experiment, it all points back to that one piece of ancient wisdom. Order and chaos aren't enemies fighting each other. They're collaborative partners, a necessary duo that works together to create the most elegant and powerful solutions.
And that kind of leaves us with one final thought, doesn't it? We spend so much of our lives trying to avoid chaos, trying to force everything into a neat, rigid order. But if this theory is right, if the most beautiful, optimal states in the universe can only emerge after a full and total exploration of chaos, then what exactly are we so afraid of? Maybe chaos isn't the end of the road. Maybe it's the only way to truly begin.